Okay. Now we are going to spend next 30 minutes writing a effective Palace kernel to improve the performance of the simple attention mechanism, which plays a critical role in any LLM. So let's walk through the basics of the simple attention, and we will also write a simple JAX code, then replace that JAX code with a custom Palace kernel. Then we will talk about how to tune that Palace kernel and why do we need it, and why can't XLA compiler help us to do what we are actually trying to achieve using a custom Palace kernel. Okay, those are the few things we are going to cover in the next 30 minutes. Okay, let's look at the simple attention mechanism. And if you look at the attention mechanism, it's super simple in the sense all we are trying to do is let's say if you have in this example, we have 8 query tokens. Rather than having a bigger context, we have a very small context, 8 tokens, and we are actually trying to attend each token with respect to every other token. That's all we are actually trying to do here. So now if you look at when you look, where is the pointer? Yeah. So the entire attention is, that's it. Visually speaking, you have the queue. That means these are the 8 query tokens, and each token is represented by some dimension, embedding dimension. It can be a 3072 or maybe 8168, whatever the model dimension you have. In the GPT case, that is either 2880 or 3072, depending upon padding or not padding. So now these are the 8 query tokens, and these are the equivalent representation for keys. Then you are actually trying to do a matmal between them. That means you are actually trying to understand how similar with respect to each other, and you are getting a attention scores, and you are actually doing a little bit scaling based upon the embedding dimension of the model. Then you are actually applying a softmax. Then you are using those scaled factors as a weighted sum on the value vectors, and eventually you are getting a representation for those 8 query tokens. That's it. That is the entire attention mechanism. And if you really look at the math, you have the one matmal, QK transpose, and we have a softmax. Then we have another matmal. So essentially, there are only 3 operations we have: one matmal, softmax, and another matmal. And of course, I'm also ignoring the causal mask. So that means after applying the softmax, you are also trying to apply the causal mask. Causal mask is nothing but, okay, you are not trying to peek into the future tokens. So that's where you are actually applying a causal mask, which is nothing but just masking all of these scores. Let's say query 1, let's say query 2 should only attend with the query 1 and query 2, and it should not attend with respect to any other tokens. That's how they're all actually masked. And finally, you are going to normalize based upon this mask, then multiply, use them as a weighted scores on the value projections, and eventually you will get the output. So that's what you have here. And the little bit more is multi-head attention. Let's say if you look at the GPT OSS model, instead of having a one attention mechanism, we have 64 query heads. That means you are actually having a 64 QKV, and each one is applying a different attention mechanism based upon each head. So that's what you have. Nothing. You are just doing a vector VMAP on top of the simple attention mechanism. And let's look at another one, the group query. This is the most important. Earlier, I talked about 64 query heads. And if you also have the 64 KV heads, the computation is going to be super expensive because every query head, every KV head. But in the group query attention, multiple query heads are actually sharing the KV head, which essentially reduces the number of parameters on the number of parameters, and as well as the computation also. So that's the group query attention. So in case of the GPT-OS model, we have 64 query heads and 8 KV heads. That means 8 query heads are actually sharing the 1 KV head. So that's it. You have a simple attention, you have the multi-head attention, and group query attention. Those are the only 3 concepts you really require to look at any of the attention mechanisms in any of the open source models. Okay, let's look at let's say if you want to write this attention mechanism in the JAX, okay, how do you write that attention mechanism in the JAX? Most of the code is very boilerplate code, but let's look at this attention mechanism. What you have, one is a logic. Basically, you already have a matmal between QK transpose. That's the one statement. This is ignore all of these ones. And we also have there is a online softmax. Let me talk about what is online softmax. So then you are applying a softmax. Then you are once you get the scores, then you are actually multiplying with the value vectors, and you are actually getting the output. So this is the JAX code with a few additions here. Okay, what is the additions here? Let's talk about what is online softmax before we dig deep into the these 3-4 lines of code. Okay, let's talk about the online softmax. Okay, what is online? Okay, when you look at the softmax, this is the technique NVIDIA actually published maybe 4 years ago. No one actually cared until 2023. Then this technique became very popular in 2022 when everyone is talking about LLM. But this technique is actually introduced by NVIDIA for a long time ago. So, okay, what is the challenge with the softmax? When you have maybe 10, let's say 8 scores, attention scores, you can have a big range, because when you have the softmax, you are actually doing a exponential normalization. So that means you are taking every score and you are doing a u to the power of that score. Let's look at there are 8 numbers, and if one of those numbers is very big, let's say 10,000, then what happens? U to the power of 10,000, it's going to have a very big number, then which is going to introduce all kinds of numerical problems. So the way you can elevate that problem is, okay, take that max number out of those 8 numbers and subtract that max number out of every number and do that exponent, then sum of that as a denominator, then you are going to do the normalization. So that means all you are doing is you are trying to find what is the max out of that logic scores and subtract that max score out of each of those numbers, then use that result as a exponent, the exponent of that result, and then sum it up and use that as a denominator and to normalize the scores. That is the online softmax. And there is one more, that is the numerical stability technique. And there is one more technique we really need to understand online softmax. For example, okay, when you do the when you do the softmax, how many loops you are actually doing it? First, you are going to the exponent each number. That means you have to run a one loop to compute the total sum. Then again, you are going to run another loop and dividing each number divided by the denominator. That's what you are trying to do here. But let's say when you look at our MATML, how did you do it? MATML, you are always doing a block-wise MATML. So that means even can you actually do a block-wise softmax computation? That is the trick you need to apply if you want to do the softmax. Because if you really look at the softmax, we don't want to compute all the scores and do the denominator, then divide each number. Can you actually work block by block? So that means, for example, you have 8 numbers. And let's say if I want to do the softmax on the first 4 numbers, okay? Then remaining 4 numbers, then how will you do it? That means you have to really keep track of what is the max number you computed the first 4 numbers, and you also compute what is the denominator you computed the L. Then when you move to the next block, let fix whatever things you actually did previous one. Basically, you are going to multiply it back because you divide it, because whatever denominator you use, that is a partial denominator. But now I have the full denominator. Let's fix the previous computation. That means you are multiply by the whatever denominator you used, then use the new denominator to divide it. So that is the technique we are going to use while implementing your block-wise fused attention kernel. Other than that, there is nothing more than that. The XLA compiler won't be able to do it because that is a math technique you are actually using to break the computation. So that's the reason XLA compiler won't be able to perform whatever optimization you are actually trying to do, because the compiler, you cannot really inject your algorithm knowledge in the XLA compiler. It can only operate at the operator level. You are actually using a simple math technique to break the softmax into the block-wise softmax. Okay, now let's look at this is the one, okay. Now if you look at, that's what we are actually trying to do here. If you do the logic scores and you are actually computing the max and you are subtracting that max out of each number, then you are doing exponent, then you are actually doing a sum, and you are dividing the scores divided by the sum. So these are the 5 statements we just talked about, and those are the 5 lines of code. Then finally, you are actually using that scores and multiplying with a V, then you are getting the attention. So these are the few steps to compute the attention mechanism. Okay, now given this attention mechanism which is implemented in the JAX, now let's say once it goes to the compiler, and eventually if you do the XPROF, it is going to do some 3 it is going to fuse a lot of operations together because as I said earlier, the fusion in the sense, for example, when you are trying to compute once you compute the logit scores, we don't want to write that logit scores to the HBM in order to compute the max because I already have that information in the VMEM, or maybe if that information is already there in the V registers, I can immediately compute the max as part of that operation. That's how the XLA compiler is actually fusing a lot of ops which you have written there into the one single op, and which is trying to make it more effective while running these programs on the TPU. That's where XLA compiler is actually come into the play, which is actually looking into the entire computational graph, and it is trying to fuse multiple ops. What is the goal? We really want to utilize the bandwidth between HBM and VMEM, and we want to reduce the round trips between VMEM and HBM because that becomes really costly. If the intermediate data is already available in the register or VMEM, let's do a little bit more computation before you write that information to the HBM. So that is the key things coming from the XLA compiler. So now if you look at, if I look at each of these ones, okay, fusion, it is actually trying to do these operations together into the one single op, the XLA compiler. So now you can actually go dig deep into click on it, and it is going to tell you, okay, which operations are actually fused together, okay, how much performance gain you are getting, and roofline access, roofline matrix, and so on. So that's where the power of XLA compiler come into the play, and it's immediately you can recognize, even though you are writing a few lines of code, but how XLA compiler is effectively fusing a lot of operations together to get a best performance out of the TPUs. So that for these operations, you can actually look at, okay, how much time we are actually spending on the flops utilization, okay, HBM bandwidth utilization. If you really look at these operations, you are only getting the 24% flop utilization. Okay, now if you look at this one, maybe flop utilization very, very tiny because you are actually trying to use whatever, this max logic are very simple operations. But again, here, utilization 21, 69%. So now you can look at the flop utilization very clearly because you actually have exact inputs to each one of them. Then we have to really, then you have to really talk about, okay, in order to improve this flop utilization, okay, should I really increase my input sizes so that we can actually perform more compute for the data you are actually moving from HBM to VMEM? That's where a lot of things come into the play. Okay, what is the right batch size you need to use? And then using these X props, you should be able to tune some of these terms. Now we are going to take this one and we are going to improve this by writing a custom kernel code for this just simple attention mechanism.
So one question here. So this underlying idea is the flash attention. Is this the mechanism is the one that automatically incorporated with the XLA? This is the what?
Yeah, so flash attention, you are actually writing a custom attention kernel.
Okay.
Because even though you have written this attention, it actually fused as many operations as possible in the XLA compiler.
Yeah.
But it doesn't really know how to really do the online softmax because block-wise softmax.
Correct.
That is actually algorithm. Unless we really introduce that algorithmic knowledge inside the XLA compiler, it cannot do that. Then you are actually crossing the boundaries. Okay, what is so should compiler actually know? No, it should not really. That means you are injecting, okay,
predetermined or
okay, maybe the user doesn't want to do that. Maybe something else user wants to do it because that means you are actually acting on behalf of the work, on behalf of the user. Okay, I know better way to implement. Maybe I don't want that kind of implementation. So that means we cannot really introduce algorithmic knowledge inside the XLA compiler. You should only, okay, these are the operations because we're already exposing a certain operation by XLA compiler, like a exponential or maybe matmul or maybe XYZ operations. So only we are going to reorder those operations or maybe fuse those operations. That is the responsibility of the XLA compiler. It should not introduce some other than, it should not introduce one more op in between, which I didn't even write.
Sure. It's automatic cache optimization in principle. Yeah, sure.
Okay, now we already talked about it. Okay, this is the beautiful visualization. I think this is a very good blog post if you want to read it later. Okay, so now you are already familiar with the structure of the computation, how you really want to break. So this picture is similar to the what matmul we did it. Yes? So now if you look at this one, this is the number of query tokens. For example, you are doing attention with maybe 4096 tokens. That's the sequence length. So that means we have to make it a little bit easier, okay, 1024 tokens. We have 1024 tokens here, and there are 1024 tokens here. So what is the shape of the attention matrix? 1024, 1024. So that means 1024 is a million numbers. So if you don't have a future kernel, first you are doing a QKT transpose. That means you are computing a 1 million numbers, and you are writing those 1 million numbers to the HBM. Then you are actually doing all kinds of intermediate computations, max number, blah, 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 softmax. Then you are reading that 1 million numbers again block by block, and you are actually doing the normalization. Then again, you are actually having another 1024 V dimension vectors, 8 dimension vectors, and you have to multiply them. So that means you have 3 distinct operations. What we are trying to do is we are trying to fuse all those 3 distinct operations into one operation. So that means we are going to operate block by block, fusing all those 3 operations together on a single block. So now let's say if you look at this, the queue, let's say if you're working on this one block, let's think about this 128 tokens. And these 128 tokens are multiplied with 128 tokens. So that means you are getting a small attention matrix, 128 by 128. So you can do it very quickly because you move this block from HBM to VMEM, you multiply this with this, you got the attention scores. But now I'm going to do the softmax on this itself. Because ideally speaking, to do the softmax, you need to compute all these 4 blocks before you run the softmax. But now, as I said earlier, we are actually breaking the softmax into the block-wise softmax. So that means we are going to do a max and as well as a denominator based upon these scores. And we are compute these attention scores, and we are going to multiply with that this one, and we are going to store this one. Even though those multiplication factors are wrong, but those multiplication factors are correct based upon these 128 numbers. So you have the partial result here. Now you are going to move to the next block. So now you go to the next block, and again you are going to compute attention scores. But now you also maintain the stats based on the previous block. Okay, what's the max number you observed, and what is the denominator based upon the previous block. Now we are going to see the current max, and we are going to compare with the previous one, and we know what is the most up-to-date max. And we can also recompute the denominator, because earlier you used this denominator, but now that denominator is wrong. So, but we already know what is the previous denominator we have used, and we are going to fix that problem. So because that means we are going to multiply with the same denominator so that we can get back to the previous one, then divide by the most recent denominator, that is previous one plus current one. So that's how we are actually doing a blockwise softmax. Okay, what is the key idea here? So that means once you finish these 4 iterations, you computed the most the accurate estimation of the O. After that, we will never visit this block again. So that means we were able to keep everything in the VMEM. There are 3 things that are happening. One is we never materialize the entire attention matrix, 1 million by 1 million, because we are always working block by block. That means we have a small block attention matrix, and we just maintaining a few small stats. Basically, what we need to maintain, what is the max number so far we observed for that row, that means 1 number. So that means 128 rows, we are just maintaining 128 numbers. And at the same time, we also need to maintain what is the denominator so far we accumulated. So there is another 128 numbers. Using those 128 numbers, we are able to move from here to here, here to here, here. Then once you complete this entire row, then we can actually write this one back to the HBM. So that means that block is actually completed, and we are actually writing from VMEM to the HBM. So we never visited HBM in between. So that's what we really mean by the fusion. That means we are actually fusing multiple operations at the block level. Then we compute all the necessary computations just based on the VMEM and the registers and whatever compute units you really need. And at the end of the day, you are able to compute attention without materializing the full attention matrix. Any questions so far? That is the key idea. Then we will make it more advanced techniques later. Yeah. Good. Okay. Now Okay, at least we got the idea. Okay, how will you implement this in the Palace kernel language? Okay, how much code you need to write to implement this? Okay, this one summary. Okay, okay. All I said is exactly on this slide. Not even I didn't even omit any line of code. Basically, what we have is this is the kernel code we are actually writing, Palace kernel code. Okay, what did we have? This is one initialization step because every time we start a new row, we have to initialize your accumulation buffer, and we also need to initialize L and M. That's it. That is initialization. And here we have the QK transpose, and here we are actually computing what is the current max. And we are actually trying to compare with the previous block M max. We got that one. And this is what we really want to see, okay, how to fix the previous computation. That means we need to remember the previously accumulated L so that we can multiply it, because earlier we divided. So you multiply it so that you can get the original. Then you divide by the most current one. So that's one. Then you do the multiplication. And to make it a little bit more efficient, do the division only at the end. You don't have to divide in between, because that's waste of flops. If you divide it, then again you have to fix it again. So just you keep tracking of the most recent denominator, that is L next, and use that L next at the end. So this is the entire kernel you've actually written. Okay, now you want to apply this block by block. That means you need to have some outer layer which is going to apply this kernel block by block. So now let's look at this is what we have, entire thing, in the sense, okay, this is the kernel, and this is what we are actually trying to specify, okay, how to divide your input, the block by block, and finally these are sample inputs and run it. Okay, let me walk through simple visualization so that you can really understand here. Okay, let's say we have the Q, so that I can use the different block sizes on the Q and different block sizes on the K and different block sizes on the V. Okay, let's say here we have input is 4096, that many number of tokens, and I took a little bit different dimension so that you really understand. This is the 192 is the head dimension. So that means we have a 4096 tokens with head dimension is 192. Okay, so here we also have obviously this has to match with the K dimension 192 and 4096. So, and here I'm using a block size is actually 1024. Here I'm using a block size as a 2048. So that means for every block, for this one, we need to have 2 iterations. Multiply with this one, keep track of the L and M, then this one, then we move to the next block, then use the previous iteration, use those ones, then multiply with this block, and you get this one. So then repeat the same thing across all the rows. So that's how you have just implemented the entire attention using a block-wise attention. You just split your computation into the block-wise computation, and you are actually fusing all 3 ops together at the block level. So earlier, now try to compare this code with the original JAX code. Original JAX code, you didn't even have any control how to really fuse the ops together, because you are actually relying on the XLA compiler to do the certain fusion of operations. But here you actually introduce the online softmax, block-wise softmax, and you are able to write a custom kernel to implement a fused operation of the entire attention. Basically, the QK transpose, max, the exponent, the denominator computation, and multiplying the scores with this one. Any questions so far? So the main idea is it is not that complicated. As long as you have a few good handle of the few concepts, how to specify your input using the block spec, and how to specify the grid, and write your kernel using a regular JAX operations, and you should be able to write a custom kernel to improve the performance of the certain fused operations. This one, okay. The sequence, okay. Let's talk about how to make it as a little bit more parallelized. If you look at the TPUs, we do multiple cores on the TPU. Sometimes we have the 2 cores. In the 2 cores, that means we can actually schedule this row on another core, this row another core, this row on another core. So that means that's how we actually try to parallelize these computations across multiple cores. But we try to avoid doing the parallelization of this one, because if you try to parallelize this on across multiple cores, then you have to really remember the synchronization between those two cores. So we don't want to do that, because that's how we try to tell the compiler, okay, do only parallelization across these rows, don't do the parallelization across this column wise.
And also, if it's within the two cores of the same CPU, then the race conditions, all these things will also be there.
So that's why we are trying to make it as simple as that,
Always.
so you don't even have to worry about
The race conditions, that's why you're trying to put it,
Yeah. Because you already have a lot more room to parallelize. You don't have to parallelize everywhere, because you already have 4 rows, and if you have the 2 cores, you can actually run these 2 on one core and you run these 2 on the other core. You don't have to really worry about it, because you just have one instruction here, compiler. Maybe I didn't write it here. Maybe here we can say the compiler, then we can tell which grid axis you want to parallelize, which axis you don't want to parallelize. Then automatically XLA compiler is going to do it for you. Okay, now let's look at the little bit more interesting aspect here. When you look at a causal mask, okay, if you don't optimize, you are also wasting a lot of flops, doing a lot of unwanted computations. So then how can you actually improve this existing kernel? Because even the XLA compiler won't be able to do it for you, because XLA compiler is simply, when you do the QK transpose, it doesn't matter whether it's zeros or whatever it is going to do the QK transpose. But here we have some interesting domain knowledge about our problem. Because if you look at our QK transpose here, when you look at the casual attention, let's say, for example, we have 8 rows and 8 tokens, and we are supposed to compute only once. We don't want to compute zeros. Agree? Because in the causal mask, you should not peek into the future tokens. So if you look at this row, this is the only valid computation you really need. You don't have to really do the computation for these blocks. There is no point of reading these blocks from HBM to the VMM and do the QK transpose, which is anyway zeros. Then after that, you apply the minus infinity masking. Basically, you are doing a lot of unwanted computations if you don't take advantage of the sparsity in the QK transpose. So now, how can we improve the existing kernel to accommodate this knowledge so that we can actually skip some of the blocks? We don't want to multiply those blocks. So that means earlier what we're doing is, if you don't have this interesting structure, you are actually working this one, multiply this one, then this also multiply with this one. Basically, you're doing 4 iterations here, but which actually requires only 1 iteration. Agree? Because we really want to skip these through. So that means we really want to build some metadata, and we want to use that metadata to skip unwanted computations in the Palace kernel. So as long as I can do a small utility to compute which blocks to ignore and which blocks to keep it. Because if you really look at, there are 3 color codes here. This yellow code, we don't even want to do any computation. That means we don't even want to move them from HBM to the VMM, because there is no point of doing anything. And these blocks, we really need to apply some partial attention. And these blocks, we need to apply their full attention. So we just want to, let's say if you want to have let's say this block size, if we want to maintain 4 by 4 numbers, which actually encodes what is the type of the block, and we can use that information in the attention kernel, and we can skip. And that's where the small auxiliary data structure we are going to build, and we are going to keep that auxiliary data structure in the SMEM, which is going to be very, very useful. Earlier we talked about VMEM, and we also talked about SMEM, which is very, very fast, and we can actually keep this auxiliary information in the SMEM, and we can actually use that information while walking through the Palace kernel computation.
Does this control of storing in the VMAM and SMAM will be with the developer, or?
Yeah, it's a developer. You can control.
But will it automatically handled by the compiler as well? Because not necessarily all developer knows that what data set should be put in there. Or not.
So that's where this Palace kernel is actually coming to, because you are saying I want to take things in my control. So we are giving you all the APIs, okay, how to access SMAM,
so
how to access the VMAM.
If I've taken this control, then it is my responsibility.
Yes.
It won't. Okay.
Yes. It's basically, it is giving you the opportunity, and you can specify where do you want to keep this information, because it is intermediate auxiliary data structures you computed to make it more effective. then you have option of putting them in the SMEM, you can putting it in the VMEM, and obviously this is a tiny data structure, and you want to put them into the SMEM. Yeah.
And this is only the read only or write back?
You can write it also.
Write it also.
Yeah.
Okay.
Because let's say if you're trying to have the double buffer, yeah, we can do a lot more interesting things.
Okay. And what happens if I overload with this? The previous one automatically will be stored right back, or will it be thrown? How
So you have to. It really depends on whether you need a double buffer or not. Then yes, we have to.
But all these things the developer needs to take into control.
Yeah.
Okay.
So now, okay. So now that means we need to write a little bit more code because we want to improve. So that means we want to improve in the sense we want to skip unnecessary computations. So that means we have to build a small data structure. Of course, we are going to spend a few cycles to compute that data structure. That's going to be tiny data structure. In this case, okay, these are the few data structures I'm computing, okay, encoding and, okay, which block I need to traverse, which blocks I need to ignore, and so on. So using these simple data structures, and we are going to push them into the SMEM, and we are going to make use of them in the attention computation. So at least, hopefully you got the core idea, then we will look into how it is actually implemented. And this entire code is available on the GitHub. It's not like any secret or anything. It's available on the GitHub, and you should be able to try it on a simple Colab. You don't even have to run the big large language model. If you want to try it out, just copy this code and go to the any TPU. It's a free available, and just copy paste and try it, run it, and make small changes and see how it actually works. Okay, so these are the data structures we computed, and we are actually going to copy them into the SMEM, and we are going to make use of them while doing the attention. Okay, now let's look at how this I just put the entire code on the one single slide. Okay, now let's look at what's happening here. So now this is the actual Palace call. When you look at the Palace call, this is the actual kernel which is going to be executed, and we have the bunch of arguments. And we are also trying to pass, okay, this is where we are actually trying to specify, okay, what are the additional data structure we need to copy into the SMEM. That is the number of scalar prefetch is 6. That means those are the ones we actually computed, and these items are going to be copied into the SMEM. And here we are actually trying to specify the scratch space for M, L, and O. Okay, then you can actually say, okay, I want additional buffers in the VMEM to store my intermediate results, L and MO. And we are also trying to specify, okay, these are the additional 6 data structure, auxiliary structures we computed, and these items are going to be copied into the SMEM. And it is also trying to pass the bunch of other input information. So that's the entire input, the Palace call structure. Now let's look at the attention kernel. Okay, how are we going to make use of these auxiliary structures in the kernel? Yeah, so we already talked about grid definition. That means how many times we are going to run this program, because we are going to run how many heads we are having and what is the grid size. Then we have the git definition, and this is SMEM input, that is the scalar memory. That's where we are going to push, okay, which blocks to ignore, which blocks we need to compute full attention, and so on. And these are the VMEM inputs. That's where your blocks from Q and KV are actually copied from HBM to the VMEM. And what is the size of these blocks? Those are going to be determined by your BQ and BKV. So BQ is going to decide, okay, how many rows you are going to pick from the Q, and BKV is going to decide how many rows you are going to pick from the K. Those are the block sizes for Q and V. So now we set up the entire Palace kernel, how to split our input data structures, and where to copy the auxiliary structures, and where to create the scratch buffers for L, M, and O. Okay, so yeah, so okay. This is where, visually, so now I just this is the TPU architecture, yes? That's what we are familiar with it. So this is where HBM, and this is where we have all the inputs, Q, K, V, and everything is actually available in the HBM. And we are actually, based upon our BQ and BKV sizes, we are pushing blocks from QKV from here to the VMEM. And all the all this, the auxiliary structures we computed, we are actually pushing all of them into the SMEM. So we are actually set up everything now. Okay, we have the input, and the blocks of the input is available here. Auxiliary structures are available in the SMEM. Now we are going to look into the actual code, which is going to operate on these blocks, and using these data structures, it is going to move these blocks into this MXU and all the other computational, like computing the max and applying the exponential on the scores and summing up and denominator and so on. Okay, this is the code. If you really look at, it's not that complicated. So entire kernel you can actually write in maybe 200 to 300 lines of code, and most of the code I actually pasted on these slides. 90% of the code is actually there on the slide, and you can look at the GitHub and you can actually copy this code and you can run it in a Colab. So everything is, that's what you have. If you look at how basically using that mask information, whether you want to skip it or not. So especially what the key idea is, when you do the matmul, let's say if you're working on the current block, you are already telling the underlying compiler which blocks to bring from HBM to the VMM. Now here I'm going to tell, because I know which block to be skipped, I'm just tricking the underlying Palace compiler, okay, what is the next valid block, so that it is going to bring only the block which is not zeros. That is the trick we are actually using. That is the whole key idea behind it. That means you just need to tell Palace, okay, what is the next valid block? Okay, how can you tell what is the next valid block? Because you already pre-computed a small data structure, which is the valid block and which is not valid block. And that's how we are actually trying to avoid bringing 0 blocks from HBM to the VMM, and we are completely avoiding doing those computations. Any questions so far? I know it's very fast-paced kernel, but I really want to make sure that you get the key ideas, key principles, and you also have a glimpse into the code blocks rather than just doing a little bit the presentation. Any questions so far? Good. Hopefully, as long as you're getting the key core concepts, that's good. After that, you can actually look at the code on the GitHub, and you can copy that code, and you can get one single TPU and run it. Okay, that's what we really talked about is control flow, initialization, accumulation, and final write. Those are the 4 sections. We already talked about it, and we actually do a little bit visualization here. Okay, any questions so far? Okay, I'm going to skip, in the interest of the time, backward pass, and we can also do a custom kernel for backward pass. Okay, why backward pass? Okay, maybe let me spend 1 or 2 minutes. Okay, what is the backward pass? Once you compute the forward pass, then obviously we really want to compute the gradients of the WQ, WK, and WV. Those are the gradients of the weights, and we should be able to update those weights based upon the whatever accumulated gradients we. So in order to compute those gradients, first you need to compute the gradients with respect to the DV, DQ, and DQ. These are the gradients you need to compute. And again, those are again bunch of matmuls, nothing more than that, because you are actually computing the gradient of the loss with respect to V, that is the DV, and the gradient of the loss with respect to the K, and the gradient of the loss with respect to the Q. Once you compute DK and DQ, DV, then you can go back and you can compute the gradient with respect to the WQ, WK, and WV. Then you can apply the whatever optimization you have, and you're going to perform the weight update. So that means in order to compute these gradients, DV, how will you compute the DV? It's basically, it is going to have another matmul here, P transpose. Okay, now the question is, why do we need another custom kernel for doing a backward pass? Because again, we are dependent on attention score matrix in between. Because attention score matrix, we don't want to store entire attention matrix during the forward pass. And we are actually trying to store only few necessary numbers, basically. Then we are going to recompute that attention matrix block by block. Then we are going to use that block-wise computation again to compute the gradients. And if you really look into ignore the math post, that's not big deal. This is what it is going to happen again. So again, we have the Ks and again Qs, and we are going to do the K transpose, Q transpose, then we are going to do the accumulate dk and dv, and the same technique in the sense we are repeating the same technique, but the matmals are different while doing the backward computation. So, okay, I'm skipping all of these slides because the same idea, the same kernel, it is actually repetition. The same ideas are actually being utilized to compute the dk and dv. And once you compute the dk, dv, dq, then you go to the gradient of the wq, wvu, and wa. Okay, okay. At least we covered the basic idea behind the attention and how to skip the unwanted computations and how to fuse the multiple operations. And we also peeked into how to write another custom kernel for computing the backward pass. Okay, let's look at the mixture of experts. That is also we want to cover, because when you look at the LLM, you have the attention layer and we have the MLP layer. And we are repeating that block X number of times. That is the entire decode architecture. And we spent, let's half of the time on the attention. Let's spend remaining portion on the MOE architecture. Okay, let's see what are the challenges with the MOE. Okay, now MOE, it became very popular. I think Google introduced the MOE architecture a long time ago, maybe 2021, but it was popularized with Mistral. After that, everyone actually adopted MOE architecture in every model architecture. If you look at the GPT or DeepSeek or Qwen, all of these models are having the MOE mixture of experts architecture in the MLP layer. Okay, what's the reason? We are actually increasing the model size, but at the same time, we are also reducing the inference cost, because that is the most important thing. Even though you are expanding the model capacity, but we are also, we are not paying significant cost for doing the inference, because each token is getting routed to the only a few experts, not every expert. So that's the reason the amount of computation is going to be smaller, but the total number of parameters are actually huge. Because let's say, for example, you have 128 experts. That means you have 128, 3072, 30072. That's a weight matrix you are trying to have in the GPT. But every token is not going through all 128 experts. Every token is going through the only 4 experts. So that means the amount of computation you are doing is much smaller. Each token is routed to either 4 or 8, depending upon how many experts you are trying to choose. But the total number of params are huge. So that means you need a lot of device memory to store all of those params. But at any given point of time, each token is being routed to only few experts. Okay, let's see the challenge we have. So this is the picture you can see. Look at this one. These are the tokens, and each token you are trying to have another weight routing matrix, because you need to choose. Okay, we have 128 experts, and we have a token. Okay, which experts should we route this token? So that means we need to have another weight matrix, which is going to, or we call it the routing matrix, and we take the model dimension, you are going to pass through that weight matrix, and it is going to give 128 scores, and we are trying to do some normalization, and we are trying to find the top K out of those 128 scores, and that's how we are going to route this input token to the 4 experts. That's great, but now after that what happens? Because as I said earlier, these experts are not sitting on every device, because if let's say 128 experts, you don't have all 128 experts on a given device. You have only maybe 8 experts sitting on this. So that means we need to sort these tokens based upon which expert they have to be routed. That means we have to introduce some kind of collective. That's we call all-to-all. That means each token physically routed to whichever expert they were delegated and wherever that expert is actually residing. So that means first you compute which token, which experts each token should be routed. Then you are going to sort those tokens by expert. That means all the tokens which are routed to the expert 1 in one group, all the tokens which are routed to the expert 2, another group, and so on. Then after that, expert 1 is hosted on the device 8. You have to take that entire block and you have to route that block to the device 8 using your ICA intercommute. So that means we need to have a all-to-all protocol. So that's how your computing the routing, sorting the tokens by expert ID, and do the all-to-all, then do the local computation using the MLP, then send the results back to the original sender, then again sort by your original token ID and compute the weighted sum, and finally compute the output. So that's what happening in the mixture of experts. So there are a lot of ops, very straightforward. First you compute the route, sort by the expert ID, and do the all-to-all routing, then do the local computation, and do the reverse all-to-all, then do the weighted sum, and sum it up. So now let's see how to, if you look at the MVE layer in the JAX, it's 10 lines of code. Literally whatever I said, you write one line at a time, that's it. But that is not going to be very, very effective because there are certain challenges. How to perform these group metric multiplications. That's what we're going to talk about it. Okay, now if you look at the GPT, okay, these are the high-level parameters so that you can get some idea, okay, how big these weight matrices are all. We have 36 layers, and every layer has a MVE block, and we have two MLP layers. One is the gated MLP, and the other one is the downward projections. And we have 128 experts, and modal dimension is 2880, and intermediate dimension is also 2880. And these weights are actually sharded if you're using expert parallelism. Let's say if you're using 16 devices, and these 128 experts are actually sharded across 16 devices. And each device is going to have only maybe 8 experts. Okay, now we already talked about it, expert kernel weights per expert. Then we are actually doing the transformation. This is a transformation we are actually running on every device. We take the input, multiply it with the weight 1, then apply the Swiss activation, and then you do the another transformation x into W0, which is going to give you the scalar multipliers, and you are actually scaling these activations using these multipliers. Then finally you are going to run a downward projection. You are trying to do the another matmul. So if you look at this is the entire transformation happening in MLP is that's it. Okay, how many transformations we have? One matmul, then we have some activation on top of it. Then there is another matmul. Then you are actually multiplying these two together using a dot-wise. Then you are actually having another matmul. So if you really look at the number of transformations you are doing in MLP layer is very, very tiny, in the sense only 3 operations. But those operations are actually compute heavy because it really depends on your input size and the weight sizes. So now what is the challenge here? Let's say you are hosting 8 experts on a given device. So that means you may get maybe 1024 tokens, but those 1024 tokens are actually distributed among 8 different experts. Maybe first expert is doing maybe 200 tokens, next expert 300 tokens, and so on. If you really want to write a simple one, you have to write 8 different MLPs because each group is dependent on a different expert. So you can actually do 8 matmuls in a loop. But we don't want to do that in a loop, but we really want to write one fused matmul which can actually effectively optimize the caching, the inputs, and group weight matrices. That's where this, again, another custom kernel is actually coming into the play. So if you don't have the custom kernel, you have to really walk through matmuls, all of these transformations, one expert at a time. But we really don't want to do one expert at a time. We want to fuse all of those 8 experts together into the one op here, and all 8 experts together in one op here, and finally another op here. So that means we are actually trying to do a group metric multiplication. Okay, so now let's look at what is the key idea, what is the group metric multiplication using a simple visualization. Let's say instead of 128 experts, let's say there are only 4 experts, so that we can actually use a 4 color codes here. Okay, and these are the input, the tokens which are routed to one single device. That single device is actually hosting the 4 experts. So that means these many number of tokens are actually routed to the red experts. This is green, this is the blue, and this is the pink. So that means that the number of tokens being routed to each expert is actually ragged. That means different number. So we have to really take these tokens. We need to multiply with the this group metric, because this is the expert 0, and this one expert 1, this one expert 2, this one expert 3. Agree? But when you're, so again, we are going back to the same fundamental concept I introduced, the tiling. So because again, you are trying to do a tile-wise computation, but when you actually load this tile, okay, when you load this tile, it has a red expert and as well as a green expert. And we are going to load this block into the VMem, and first we are going to do the compute with the red block. Okay, then store it. But then again, we are not really evicting this one. We have this one. So that means we are still keeping this guy into a VMem, then we can compute that. So that's how we are actually trying to manage. So if you look at all of these core ideas, there are only 2 things we are doing. We are actually trying to minimize data movement between HBM and VMem. If you look at all the techniques I talked about, everywhere the same principle is actually showing up again and again. So that's what we are trying to do here. That means in order to do that, what we need to do, we need to maintain a little bit auxiliary structures. That means we need to know, okay, how many experts we are going to have in this given block. There are 2 experts. Okay, what are those expert IDs? So we can actually compute that information ahead of the time. That's very simple. And use that information to drive which blocks to keep in the VMem and which blocks to evict from the VMem. And that whatever auxiliary structures you are computing, you are actually keeping them in the SMEM, because I said earlier, SMEM is very high bandwidth so that you can read it much faster. So whatever key data structures you are computing and which are needed to drive the computation in the kernel, I strongly advise keep them in the SMEM so that you can have a quicker access. It's just like having those variables in the registers, something like that. Yeah.
I'm curious about the use case for, the default, suppose you use Jack's default, just-in-time compiler and so on. That seems to be far less optimal than using Palace. What are the use cases where the default works out of the box?
No, default, everywhere it is actually.
No, it works. It's just in terms of being optimal, because this seems to be, if you use the defaults, it will probably have larger computation sizes. And
okay, let me give you the. Now we actually introduced this operator as a standalone operator in the XLA compiler itself. Now XLA compiler, if you use a JAX rack dot, which is exactly doing the same thing behind the scenes. A lot of times when you're looking for this one ops, because there are certain number of ops are already implemented in the XLA compiler. And the people come up with new requirements, new ops, they may not be available in the XLA by default. So until we support those operations, because we don't really know what user wants. Okay, this became very popular MOE architecture and everyone is actually doing it. And okay, you may be writing these custom operators to improve it. Now you don't have to write this custom kernel anymore because we realized, okay, this is very important. Okay, let me introduce that as a primary op in the XLA compiler itself. Once you have the rack dot, it is going to do the same, whatever I talked, it is actually doing behind the scenes.
Got it.
Yeah.
So this is basically for the cases where innovations are happening. It's not yet in the compiler. That's the
yes.
Yeah, okay, got it.
Yeah, because obviously, if it is a primary op and it is necessary across multiple model architectures, we don't want people to write and tune them and waste their cycles. And obviously, I can't really envision what tomorrow you are going to invent. And definitely, if you want to have some custom op. And if you write that op using a regular JAX, which is going to cost you a lot more cycles, then we are actually providing you this high-level abstraction, and you can take these ideas and you can implement it.
Got it. Thanks.
And a lot of people are actually implementing the kernel fuse multiple operations together so that they can improve it. Any questions? No. Okay, so the idea is exactly the same. I'm actually repeating these concepts again and again using different examples. But if you look at what is the key idea, even after spending 60 minutes, One is the tiling. That means you have to really understand how to split your computation into the block-wise computations. And it is very important how to tune these tile sizes. If you don't have the right sizes for these blocks, you may end up having a out of memory in the VMem, or it may perform poorly because you are either moving a small blocks, but you are actually spending a tiny amount of computation on those blocks, and you are actually increasing the time while setting up and so on. So then you would need to specify how to really run this block-wise computation, what order. And when you're running this block-wise computation, you also need to specify, okay, what is the input to each of those, the kernels, so that the Palace knows, okay, which block we need to move from HPM to the VMem, and you are actually trying to specify your block size using a block spec, and you are also trying to specify which block we need to move using index map in that, okay? Then after that, you are actually writing your kernel code. So most of the time, using these few concepts, you can write custom kernels. Okay, so now let me introduce a little bit more complex use cases where you want to fuse communications and as well as the computations. So far, I never talked about any kernel which is actually working across devices. Everything we talked about, the computation happening on a single device, and we are just moving blocks from HPM to VMem, and then we performing the computation on the block we actually moved and writing it back. Okay, what if you really want to write a custom kernel which actually requires the overlapping communication between the chips and the local computation? How can we do it? So, okay, that is the idea I'm going to introduce. Okay, and if you look at the GMM kernel, everything is actually shown on single slide. So it's not that complex. Okay, once you have these ideas, then you can assemble these ideas together. And if you don't want to write code, ask Gemini. It is going to write the code for you. Just tell what you really want to write and express, okay, this is how you really want to do the block-wise, and it is going to give the entire structure, and it's going to perform the computation, and you go and defeat it. So the thing is, you just need to express your ideas using whatever language you have. Okay. Now let's look at sorry, this one. Let's compare two approaches, FSTP and expert parallelism. Let's say if you look at all those weights, there are two ways we can do the MOE architecture we can implement. Earlier I said expert parallelism. That means we are actually sharding the weights on the expert axis, and we are physically routing the tokens from each device to wherever those experts are actually residing. That means we need to have all-to-all. And there is a other way around. We can shard these weights not on the expert axis, maybe other axis, but you can actually do the full FSTP. That means you are actually gathering the weights on every device. That means you are not doing any token routing at all. So there are two ways, but each one has its own set of advantages and disadvantages. So let's do this is what we have in the token routing. So there is a in the MOE architecture, there are two things we have to do. Once we compute which expert each token to be routed, we have to do the sorting. That's where there's a token arrangement. That means we need to sort these tokens based on the group ID. So when you look at on the TPU chip, we also have another piece of hardware which is called a sparse core, which is really good at it, sorting these operations, and we actually offload this operation to the sparse core so that it can actually perform sorting these tokens, basically reordering the memory. It has a certain interesting characteristics, how to read random memory, and it's going to sort. So that's where we are going to offload some of these operations to another piece of hardware on the TPU chip. Then we are going to do the offloading also. Where is the? I can't. Maybe it's out of charge. Okay. Now let's look at I just want to make it a little bit more visual so that you can really understand expert parallelism a little bit better. So here we have a, so look at I'm using 8 devices for expert parallelism, and we are also using I don't know, with 32 devices for the FSTP weights. So the weights are actually, we can shard the weights across the devices, and we are also sharding the expert weights across the expert axis. Then using this, the mesh architecture, then you should be able to express how you want to move weights across devices and how to route the tokens between the devices, because every device is actually operating on a local batch or local the set of tokens. And those set of tokens are actually going through the routing matrix, and it is actually deciding which experts it needs to. Then after that, it is actually running all-to-all to forward it. Basically, you are actually trying to run all-to-all across that column group. That means we have a 32 all-to-all groups are actually happening. So then each group is in the column is actually participating to route the tokens. Then we are actually having a 32 parallel all-to-all groups. That's how we are actually improving the performance of this MVE token routing. Yeah, that's what we have in the sense, basically token movement, that is all-to-all, and the GMM kernel and reverse all-to-all. So, this one. Okay. Thank you. Okay. So if you want to do a little bit visualization, that's what's happening here. So here we have 8 devices on that one column, and you are actually trying to sort your tokens based on the expert ID. And if you look at this one, okay, all the green blocks of data across all devices are actually coming back to the device 0 where those experts are actually sitting. So once you route the tokens to the designated expert, then you are going to perform the MLP on here. Then you are going to do the reverse dispatch, the results back to the wherever those tokens came from. So that's what the all-to-all is actually doing. Basically token routing, then do the MLP, local MLP, then again reverse all-to-all so that we can dispatch those results back to the originators. Okay, so any questions so far? Okay, let's cover maybe another, how much time I have? 10 minutes? 15 minutes, okay. Let me spend 15 minutes on because I covered at least core concepts, how to train these large language models using custom kernels to effectively improve the performance of those LLM. And let's talk about inference also for 15 minutes so that we can at least, because I'm, due to the time constraints, I didn't even put slides for the post-training. That is also more interesting, 2NX. Maybe sometime later we can actually spend maybe 2-3 hours how to do the post-training once you have the foundation models. Okay, how to apply all of these, the 2NX algorithms, GRPU and so on. But here I'm just assuming you already done some kind of post-training on the large language model you already trained, and now you want to serve these models. Okay, now VLLM is a very, very popular inference framework, and which is open sourced. And you can also run these models either on the TPU or GPU, depending upon the availability of the resources you have. So now let me talk about VLLM with focused TPU inference. Let's say you have a model trained GPT-OSS model, and you want to run the inference. Okay, now let's look at how does the inference look like. The inference is actually a combination of the two phases, the prefill and generation. Let's say, obviously, every day you are actually interacting with either Gemini or ChatGPT, so you are actually putting a prompt. Yes, maybe you are typing a prompt, or maybe you are uploading a document or whatever it is. So that means you are actually providing a big context. So that means we need to process the context. That's what we call them as a prefill. Then after that, once we have the context prefill processing, then we are going to generate one token at a time. So that's what it's called a generation. So there are two stages, prefill and generation. Okay, what are the challenges here compared to the training? The thing is, we are actually generating a one token at a time after the prefill phase. So there are interesting characteristics of the computation here. Prefill is going to be the compute bound, and generation is going to be the memory bound. You have to really pay attention to that, because prefill, you are actually working on entire prompt in one go. Because let's say if your prompt is 4,000 tokens, I have enough input to saturate my compute power. So that means we are actually running a full attention, 36 layers and MOE, and we are actually computing the token representation for all those 4096 tokens. Agree? Because that's just like a training job. You have a lot of input, and you can actually make use of all of the previously learned concepts. You can run the prefill. But look at the generation. Generation, what you do, let's say 4,000 tokens, you take the last token, and you are actually predicting what is the next token. That is the 4001 token. Now, once you have the 4001 token, then again you have to go through the entire model to get the representation of 4000 token all the way up to 36 layers. Then you have to get the next token. So that means what is the input in the generation stage? You have only one token. But in case of the prefill, you have 4000 tokens as input. You have a lot of input is available to saturate the compute. But that is not true in case of the decode, because you're actually working one token at a time. So to improve the performance of the generation or decode phase, we actually pack multiple requests. That means we are not going to work on a single request at a given time. We are going to pack maybe multiple users into the decode phase, so that we can actually have a more number of the tokens available as input to the decode. So that's how it is going to look like this one. This one you have the prefill, and we are actually generating one token at a time, other token at a time. And there is also, if you are a core LLM developer or inference developer, you might have heard about KV cache. That is very, very important to understand what is the meaning of the KV cache here. That means when we look at the keys and values, you already computed all the 4,000 tokens. But when you're actually trying to do the decode for the 4001 token, you don't want to really do the KV computation for all these 4,000 tokens again, because we can keep them in the cache, and we can actually use them to compute your attention layer for the 4001 token. That's what is the KV cache. We keep updating the KV cache whenever you are producing a new token. So now, given those two concepts, basically for the KV cache, that's where we are actually trying to allocate these KV caches using the pages. That means it's just like a regular OS. So you have a lot bigger HPM, and you are dividing that HPM into the pages, and each page contains X number of tokens. And we are actually allocating a page by page rather than allocating a fixed block of memory for the entire KV cache. So that means whenever you need, you are going to get a 1 page or 2 page, and each page is capable of storing maybe 256 tokens. So that's how you have these pages. Now how does attention work? It's going to be page attention. In the large language model training, all the KV tokens are actually in the contiguous memory. But here, the KV tokens are not in the contiguous memory. They are actually spread across multiple pages. So that means you need to have some kind of custom kernel to get all the KVs which are actually spread across multiple pages. That's where the custom attention or paged attention, which is going to come into the play. It's the same concept, but only difference is your KV tokens are not available in the contiguous memory. So that means you need to have a explicit read from the HPM. Earlier, if you look at the earlier Palace calls, we never read explicitly, because we always gave that instruction to the Palace call by specifying the block spec. So you never wrote a explicit copy operation from HPM to the VMem. But in this case, you have a different architecture, in the sense you decided to store these tokens in a non-contiguous memory locations, but you cannot really express that using a simple the API abstractions. That's where the async IO is going to come into the play. Then you have to really write a custom page attention kernel. Okay, how to read those pages. Okay, now let's. This is the more important thing. It's a continuous or dynamic batching. As I said earlier, prefill is compute bound. Generation is a memory bound. unless you actually batch more number of requests in the decode stage, your MF utilization is going to be terrible. So that's the reason we try to batch more number of requests in the generation phase. And sometimes we also, because then we also try to mix prefill and as well as a generation decode requests across multiple users into a single, so that we can actually improve the utilization of the chip. So those are the standard techniques, but at the end of the day, you have to write a little bit custom code, how to make use of these continuous patching, especially from a kernel's perspective. Okay, let me continue the same model. Let's say we already trained the GPT-120B model, and let's say if you want to solve this model, and I'm just trying to use one simple example here. Let's say you have a context is the prefill is 1K, and I'm trying to do the 8K decode. And using that example, and I'm also trying to use the number of concurrent requests is 256, and we can use this setup to walk through how this inference actually works. Basically, we have the prefill, 1K, and 8K is a decode. And again, and if you look at the summary of the entire model, there are two operations were happening: attention and MOE. Agree? And if you look at the attention, we have the QKV projection, and we have the RPA, that's nothing but page retention kernel. Then we have the output, then we have the MOE. These are the things. But now, when you talk about the GPT-OSS model at the time of inference, you may be using a single host, maybe 8 chips. We are not really using a 256 chips or 512 chips, because for the inference, you are able to host the entire model on a single host using 8 chips. But still, you have 8 chips. That means you need to shard your model params across the 8 devices. But we are also trying to minimize the inter-chip communication. The way we want to shard these model params, we just want to have a minimum collectives so that we can run this inference very effectively. So in this case, the way we try to do is very interesting techniques we actually use. We have WKV. Rather than doing 3 different matmls, let's actually concatenate WQ and WK and WV and actually shard them across devices, and so that we can actually increase your input to the matmal, so that we can actually perform the more computations, and we can actually improve the chip utilization. So we do the concatenation WKV and shard across 8 devices, and do the matmal projections, which are sharded across 8 devices. And similarly, you are also, because remember, as I said earlier, we have a 64 query heads, and shard those query heads also across these 8 devices. So that means we are actually doing a partial query heads computation across 8 devices. But once you do the partial computation, and we are going to do a all reduce at the end to sum all the results across all the 8 devices. So effectively, we are sharding, and so this is what we are doing. We are concatenating all the weights, and we are actually running a one fused matmal, so that we can get a bigger input sizes, so that we can do the lot more compute on the amount of data you are actually transferring from HBM to the VMM. So that's what we are actually trying to do. The attention, now we have all of these KV tokens. The same attention mechanism we talked, but the only thing is we need to do a little bit more advanced movement of data, because this data KV tokens are actually spread across the pages. You need to maintain some data structures, okay, how these KV tokens are actually spread across which pages, and you need to have the page indices, a little bit more auxiliary structures to read which pages contains the KV tokens for the given request. Okay, now, so that's what we are actually trying to do, the QKV projection, and we have the RPA kernel, attention kernel, which is similar to the whatever we talked so far, and we do have the projection. Because remember, here we actually distributed computation across the nodes, which is different from FSTP. In the FSTP, we are actually gathering the weights on each device. Then we are doing a full matmal. But here, we actually sharded weights across devices, and we also sharded computation across devices. But at the end, we are going to run a simple all reduce to gather all the results. So now I think you can see the difference between the FSTP and tensor parallelism here. Because I just took a various examples so that I can actually illustrate all the core concepts. Okay. Any questions so far? I think we have 2 minutes. Let me complete this one. The same mixture of experts. In this case, I'm not really using the expert. Okay, please.
Yeah. So my question was related to the token routing. I just wanted to understand.
Yeah.
Like when first we have the tokens, and then we are routing them based on some top K or some algorithm.
Sure.
And then we are doing a step where you mentioned those dimensions were getting expanded from like 2800 to 880. It was mentioned there. So is the only reason we are expanding those dimensions to keep the process more compute bound, or is there a different reason to that?
So usually, see, why did I pad the 288 to 3072? That's the reason.
Yeah, like why did the number of dimensions expand? That 28, yeah, the padding.
The only thing is, see, when we try to do the benchmarking, because if you look at the TPU, it has a certain architecture, 256 by 256. So we just really want to get a better performance numbers to align with the existing hardware structure, which is not needed. If you don't want to pad, you don't have to pad. Just.
Okay. Okay, I think that answers it.
Yeah.
Thank you.
There is no reason to pad. If you want to get a best performance numbers, MF utilization for the benchmarking, then we try to do all these little bit tricks here and there to align with the hardware architecture. Yes.
Padding is primarily coming, right? You don't want to overlap with others, right? So that multiple readers, right? Things will keep on cache optimization. Why do you want to do the padding and then you understand the cache line, all those things, all those things.
Yeah. Yeah, if you go a little bit deep into the TPU register layout, hardware layout, then you will appreciate why people are actually doing this.
They use primarily for block by block, right? You not to overlap it so that when you go it, right, then information will not be available. Then again you read, right? Refetching, fetching, you want to avoid multiple requests. When you padding and exactly put it so that when new information bottom up, it fits so that no refetching is needed, multiple refetching and read and write.
Yeah, let me complete this 2 slides, then we are done. So now, earlier I talked about expert parallelism, but here I'm actually doing a MOE without expert parallelism. Basically, we are actually sharding the weights, not on the expert axis, so that we can actually do a tensor parallelism in the sense because we cannot really hold all 128 experts on every device, but we are actually trying to keep all 128 experts, but we are not keeping the full dimension on the 3072. 3072 is actually sharded across these 8 devices. That means each one is going to have a partial. So that means when you are doing a MOE computation, you are actually doing a partial computation. Then the weights are sharded in such a way that row-wise and column-wise, and eventually, once you do the partial computation on each of these devices, and we are going to run another all reduce at the end to get the full computation. So here, we did shard expert weights, but not on the expert axis. Every device is actually having all 128 experts, but it is not having a full model dimension. It is only having a partial. When you go back to the original slide, I've shown you how to shard your weights. So here we are actually sharding the weights. One is the column-wise, and the other one is row-wise, so that we can multiply nicely with the first W1. Then you can multiply with the WO, but which is going to give the only partial result on given device. But then the same tokens are actually available on all 8 devices. Everyone is doing a partial computation. Then we can sum it up. We can get the full computation. That's where all reduce is going to come into the play. So now, just doing a 2 all reduce, we were able to do the full attention and MOE, and we were able to do the inference. So hopefully you got a good understanding of the, so at least that's my presentation. Hopefully you will learn some core concepts.
Thank you so much. Thank you for the wonderful insights. Of course, I would say that these are the state-of-the-art implementations, right? One really wants to get into the world of transformers, want to build or including fine-tuning, right? If you think about fine-tuning, then you really need to know all these concepts, especially how to make use of the TPUs more effectively, right? So then you are saving time, saving cost, and as well as, right, production comes so quickly. And even when you want to invert new methods, new architectures, these are the things one should really know about it. And whatever that he discussed about the optimization TPUs that's applicable to GPUs, even CPUs also you can really go. And more importantly, not necessarily only for transformers, right? Even if you're doing other scientific computing, these techniques are must in order to exploit the GPUs, accelerator, and so on. So thank you once again for very detailed and insightful presentations. I know there may be multiple questions. We take advantage of the last presentation so that I leave it open, the floor open. Let me officially close this session, but if you have any questions that we can take it after this session, right? So let's thank the speaker once again as a token of appreciation, right? We want to give small memento just for the remembrance. Yeah, please come this. Thank you so much. Yeah, so today officially I'm closing the session. Again, tomorrow we will start with more of a scientific mission. Now we know how to do computing, what to do with the TPUs. Let us think about the algorithms and methods tomorrow, right? So let us have a break and then we will reconvene tomorrow at 9 a.m., right?